My name is Jukka Pekka Jalkanen. I come from Finnish Meteorological Institute. So I took the liberty of modifying the title of my talk slightly, because I wanted to include some of the things that we have done in a global scale also in this talk. Since the topic of this conference is also about the 2020 sulfur cap, so I wanted to include some examples of the work that we have done in that topic. So our primary tool in this ship emission modeling is the ship traffic emission assessment model, which is developed at FMI. So it's us who are maintaining the software. And the material that we are using for describing ship traffic, it comes from the automatic identification system. So that is something that is used on board every vessel. So it's a mandatory navigation aid. And we get data from various providers. If it's about the global scale, then it is a commercial provider that will sell us the data from satellite AIS networks and also on the terrestrial base station networks. If it's about the Baltic Sea, then it comes mostly from HELCO member states. So this is a lot of data. So for the Baltic Sea, it's over 1 billion position reports per year. On a global scale, it can be between 8 and 10 billion position reports per year. But I would say that the Baltic Sea is one of the best covered regions in the world in this regard. On top of the vessel activity, we also need to have the fleet description. So we need to know that how the different vessels are built. So how were they designed? How large are they? What kind of engines they're running? And this data comes from IHS. So that's another commercial database about the specifications of the global fleet. And these two are combined in this emission model. And there's a schematic representation here on the right side. So there's a lot of boxes there. So all the input data is here. So these are the ship database from IHS. This is the activity from data providers. Then we take a look at what kind of routes do the ships take. So where do they go? How do they operate? And then based on the speed entries of AIS position reports, we can do an estimate of the power used for propulsion. Of course, there are a lot of other systems than just used for propulsion. We also need to include estimates of auxiliary engine use, boilers, and systems like these. But in the end, you get a vessel-specific prediction of the fuel use and also for emissions. So these are given as a function of time. And when you plot these on a map for the whole of the global fleet, you get an emission inventory for shipping. So the output of the model is, it can be a large spreadsheet where you have one line for each vessel in the global fleet, and you get the emission inventory for that specific vessel. It can be images, so it can be maps, data layers, or it can be these large data sets for atmospheric models, for example. So if you're interested in where do the emissions go, how do they transform in the atmosphere, so there are atmospheric models which do that, and there are some talks with that topic later on today. But this process for the Baltic Sea, that has been repeated annually for the benefit of the HELCO member states since 2007. So there is an annual reporting of Baltic Sea ship emissions with this method, and that has been reported as a part of, there's a submission for the HELCO Maritime Group. So each year there's a document which contains the emission inventory for the Baltic Sea shipping for the previous year. Okay, and this is what it looks like. So I told you that there will be atmospheric models which take this data. Unfortunately not very visible here. But anyway, the moving bright spots are the ships. So there's a world map here in purple. So that's Europe, that's Africa here, South America, North America, and this is Southeast Asia here. So you may identify the main shipping routes in this. But the dots on the map, it means that for every movement there's an update of emissions from ships. So all of the ships in the global fleet are, you can separate them out from the total if you wish to. But this is the data that goes into these atmospheric models. So there's a different map for NOx or SOx for particles. This is for CO2. That's a scenario that we ran for CO2 emissions for the global shipping fleet in 2020. So this is the March from that year. And there's a reference here. So if you're interested in looking up the details of this work, you can find it from that reference. So if you are not using these moving dots on the map, but you are more using these images, then you can end up with something like this. So this is from a previous work that was done to assess what is the impact of this global sulfur cap. So if we reduce the global sulfur level in shipping fuels in 2020, so how much does it avoid this premature mortality, and where do the benefits actually occur? So you may see that, okay, these are again the shipping lanes, but then on land you have dark areas, like here in China, here in Singapore, that's in India. So these dark areas on the map on land mean that, okay, these are the areas which will benefit from this sulfur reduction. So you will see that most of the benefits are felt in India and in China. So those are very densely populated areas, and then there is also a high level of ship emissions there. So if you reduce sulfur globally, these countries will benefit the most. You will see that the Northern Europe and also North America, those are fairly empty, so that you don't see that much dark spots on the land on these areas. That's because you already have established the SECA there. So you have taken care of the problem already in these areas. So the areas which are currently not under SECA, so those are the ones which will benefit from the sulfur reduction. But this doesn't remove the health effects from shipping entirely. So it removes roughly 1/3 of the problem. So there are other parts of particles which are not connected to fuel sulfur. So you still have black carbon, you have organic carbon emissions, you have ash, things like these. And those contribute to small particles that we all inhale. Now, if we go back to the Baltic Sea, so in EnviSuM, we were responsible for these emission maps. So this is for the regional scale studies, that's an emission map for the Baltic Sea shipping, and then there are these 3 little boxes. So these are exactly the pilot areas where we get this closer look on the cities inside these boxes. So you have Greater Gothenburg area, you have the Gdansk, Gdynia, Sopot, the Tri-City area in Poland, and then you have St. Petersburg as a third pilot area. And if you zoom into these locations, these smaller images on the right, those indicate kind of the geographical distribution of ship emissions in these pilot locations. Now, you may have seen this graph before. So that's a time series of Baltic Sea ship emissions. So that's a NOx, SOx, PM, and carbon monoxide, and also the transport work. So these are from the annual Helcom reports for Baltic Sea fleet. So it starts from year 2006 and goes all the way to 2017. This year there will be an update where we will include the full-time series again, because we have a model update for the different, and there are some differences between the model versions. So we want to provide a consistent time series for the Helcom member states. And under this ellipsoid here, so that's where the biggest change was seen. So basically, the 2014, 15, and 16, that's an interesting period, because then you have this decrease of sulfur in ship fuels down to 0.1% in the Baltic Sea. And that's exactly the motivation for EnviSuM. So we wanted to see that, okay, if we go really low in sulfur in the Baltic Sea, then what would be the impact of that? Looking at the health impacts, environmental impacts, and trying to see that, okay, whether it really was worth it. Now, we heard earlier that there are several options how you can comply with the sulfur rules, and soon also with the nitrogen rules. So you can have this SOx scrubbing, so you have impacts on SOx, but also on particles. So the SOx scrubbing also reduces particles somewhat. And then there is this issue of black carbon, which I'm not going to go into details in this talk, but it will also have an impact on black carbon emissions. Also, NOx and VOCs are somewhat impacted, especially if you have this oxidation catalysts also included. Another option is to use LNG, so that's the gas option. You can choose these low pressure systems or high pressure systems, depending on whether you want to have this NOx reduction to tier 3 level, or if you want to have eliminate practically the methane even if you choose a gas engine or a dual fuel engine, you would have to be aware that there are some implications of that choice. Whether you are high on methane slip and low on NOx, whether you are eliminating your methane slip, but then you have to pay attention to the NOx reduction. So these kind of trade-offs exist. Of course, you can always use a low sulfur fuel, or if you have an access to an alternative fuel, if it's a bio-based, then that's even better. But for the NOx, you would have to either use catalytic conversion or use a combination of methods which will all contribute to emission level in such a way that you comply with the Tier 3 levels. And what was actually surprising for us is that, there was a team in EnviSuM who did the scrubber measurement on board a vessel. So we wanted to see what exactly happens with the scrubber. So how are different emission species impacted by the scrubber? And accidentally, this vessel also had an oxidation catalyst. And it was a surprise to us that it was very efficiently removing the metals and also the VOC emissions. So you don't see that much of secondary particle formation from that ship because you are removing those components exactly by using this combination of the scrubber and the diesel oxidation catalyst. Now, I'm extending this scope again a little bit. So on the top left, you have the global fleet. So this is the kind of an age structure. So how many ships were built with each year in the global fleet? And then these three images are the same kind of information for the Baltic Sea fleet. So this is for the dry cargo fleet. You have general cargo carriers, you have bulk carriers, container ships, vehicle carriers, and ro-ros here. And then you have the passenger ship fleet in here, and then the liquid cargo fleet on the lower right-hand corner. And the reason why I wanted to include these images is that, if we are thinking about the future scenarios for 2030, 2050, then this becomes relevant because IMO has set up these energy efficiency design indices which kind of regulate how efficient the new ships should be compared to the current ones. And looking at the okay, better? Yeah. Oh, sorry. Maybe it works better this way.
It's good that you breathe.
Yes. Especially if you're saving when you're talking. Yes, thank you. Now, setting these future scenarios. So one of the things that we did in the past was the global sulfur cap, but we also wanted to see what is the impact of these NOx emission control area in the Baltic Sea and the North Sea areas, and also looking at the energy efficiency requirements, so that we have these future developments according to the IMO rules. And for the scrubbers, this was an interesting exercise because adoption of a scrubber, of course, it depends on the price premium that you have between the heavy fuel oil and the low sulfur fuel. So it's very difficult to say how popular scrubbers will become in the future years. But of course, already now, there's a very feverish period of scrubber installations taking place just before the 2020 sulfur cap introduction. But in this area, so if you look at the Europe, and then we set the limit for the annual fuel consumption. In this case, it was 4,000 tons per year. So that would be a kind of a threshold value, a signal for us that, maybe this vessel would be a potential scrubber installation candidate. And if we start looking at the European fleet, then there are more than 700 vessels which could install a scrubber with this criteria. Of course, in this case, we are only looking at the European sea areas. And if the fuel consumption inside this area is larger than the threshold value, then that's the kind of a criteria for us. Obviously, if you're looking at the global scale and using the same kind of threshold, you will catch much more ships. So if you are doing this in a global scale, you will find out that there are roughly 10,000 vessels with a high fuel consumption, and that would be our potential scrubber market. So if you are not interested in installing a scrubber into a very old vessel, you are only using vessels which are younger than 10 years and have a high fuel consumption, then these 10,000 vessels would be the kind of potential candidates for the scrubber installation. Now, for the energy efficiency, it becomes very tricky because you have EEDI saying that you should improve the efficiency of your vessels depending on the build year and also depending on the ship type. So what do we assume for the annual efficiency gain in the future scenarios? So we dug up an older reference from 2013, which may be a bit outdated. At least it gives us a guideline. What is the expected magnitude of this efficiency improvements, and then trying to figure out how much of that actually EEDI covers. And this is a very busy slide, but I walk you through it. So we are operating on the global fleet from 2015, introducing these EEDI phases, starting from phase 0, going all the way up to phase 6. I'm not showing the phase 6 results in this, but this image on the right will include the 4th phase of the EEDI. So if you have this stepwise energy efficiency improvement of 10% every 5 years, you will not meet the 2050 reduction targets, or where you were supposed to reduce your greenhouse gas emissions from ships by 50% by 2050. So EEDI alone will not reach the target. And why? Okay, here we have taken a very optimistic view, applying EEDI for every ship, regardless of the ship type. So that's not true. Also, we are assuming that every vessel will be renewed when it reaches 30 years. Okay, we know that there are different types of vessels with a different kind of renewal rates, but for the sake of simplicity, we give this kind of an order of a magnitude estimate of the performance of the EEDI in 2050. We say, okay, after 30 years, the ship will be replaced with a new one. Now comes the important part. So what do you assume for the annual traffic increase? If you introduce anything larger than 1.3% on an annual basis to the traffic growth, that's where the EEDI is able to negate the traffic growth. So in the end, in 2050, with 1.3% increase every year in traffic, you end up at 0 levels, meaning that your emissions in 2050 will be exactly the same as in 2015. So no reduction of EEDI whatsoever in that case. So actually, when you're applying the existing phase 3 rules, so you end up with a 0.7% emission reduction per year. So you would need something more than 2% per year if you are going to halve your emissions by 2050. So the EEDI will only cover 1/3 of the requirement. So you will have to have a switch away from fossil fuels. That's clearly here. So even if you introduce phase 6 of the EEDI with the 60% reduction, that will not be enough. It will have an important consequence later on, because if you are going to introduce any kind of market-based measure, so let's say emission trading or a CO2 tax or something similar, the price tag of that mechanism is going to be very high, and it will be even higher than the global sulfur reduction. So if you introduce this kind of a cap and trade where you set your emission levels at 50% of the 2015 emissions, and then having this low growth scenario, you will end up with the emission levels which are 1.5 times the baseline, which means that the trade part of your market-based measure will be something around 22 billion euros per year. But if you have this high growth, which is now assumed like 3.5% growth of emissions every year, then you will end up with the emissions which are 3 times the baseline of 2015. And then the price tag goes up accordingly. And I did this calculation a couple of years ago, and then the CO2 price in this emission trading scheme was 8 euros per ton. But when I checked the last time, on April 17 this year, it was up to 27 euros almost. And then the price tag of this part will increase accordingly. So if there is an increase on this emission trading scheme with the CO ton price, it will also reflect on the values here. And we were asked to do this kind of an analysis for the Finnish fleet. And the outcome was that, okay, it's probably around 1% of these values. But it's still a significant amount of money. So you would imagine that if this kind of mechanism would be established, then the fleets of Panama, Liberia, the heavy tonnage fleets with the high fuel consumption, those would be the ones which would be impacted the most. Okay, I'm going to conclude with this slide. So what I want you to remember with this is that, okay, even with the phase 4 of the EEDI, that will not be enough. So you will need to come up with something else which is not a fossil-based fuel. We will see a large increase in scrubber installation, that's already there, but are we actually removing an air quality problem to the water phase? That's still a question mark. The impact studies of the scrubber water discharge in seawater, those are very, very scarce. You may have an evaluation of the volumes, you may have an evaluation of the quantities, but you have less analysis of the impacts. And that's something that is needed very urgently. And I would like to stress the importance of these onboard emission measurements, because the modeling can only be done if you have solid data. So we need a lot of data from these real-world measurements, especially, for example, let's say that you want to use ultra-low heavy fuel oil in the Baltic Sea to comply with the SECA rules. So we need measurements. What does it mean for the black carbon? What does it mean for the particles? So how do things change? This information needs to be built into these emission models in order to be a kind of a realistic representation of the ship emissions. Okay, I'm very happy to say that this project, the EnviSuM project that we are gathered here for, that has a lot of measurements. There's years of data to dig into. So this will be our task for the upcoming months or years. Thank you.
Thank you very much.